Alright, so we're going to do a example. I was about to do it in the last video. So we're going to use this equation. The main thing is to figure out T over T 1/2. So you have to know the half-life, you have to know the amount that you start with, and then the amount remaining, the radioactive amount remaining. Alright, so let's go over this. Let's say I have iodine 131. Radioactive half-life, so T 1/2 has been measured many times, and it's 8 days. And just to let you know, when you do this equation, the amount remaining and the amount that you start with have to be are in the same units, and have to be in the same units. And the same thing for the time. The time can be in days, it could be in seconds, it could be in years, but the time and the half-life have to be in the same units. That's important. So let's say the amount of time that has gone by is, I don't know, let's make it 48 days. Okay, so 48 days have gone by. We just need a starting amount. Let's say our starting amount is let's say M start is, I'm going to do this in, you can, well, here, we'll just do it this way. Let's say you started with 2.1 grams. All right, so 2.1 grams. It doesn't have to be in grams. It can be in. It doesn't even have to be in units of mass. It could be in units of volume. A lot of times they'll talk about units of volume, like ounces or cubic centimeters or something like that. So it can be in those. Let's do this calculation first. So T over T 1/2 is, of course, just 48 days divided by 8 days. And so now that turns out to be a whole number. Of course, it's 6. So that T over T 1/2 is 6. It doesn't always have to be a whole number. In other words, another way of looking at this is 6 half-lives have gone by. So a half-life you can just think of as a unit of time. In the case of iodine 131, the half-life is 8 days, and so 6 half-lives have gone by to reach a time of 48 days. All right, so how much remains? The amount remaining is going to equal what you started with, so it's 2.1 grams. Again, the amount remaining will be in the same units, and so it's 1/2. And it's raised to the T over T 1/2, which we've already calculated. It's right here. So that's raised to the 6th power. So this is going to be, some fraction. If you think about it, this is going to be some fraction times the initial amount. All right. So what I'm going to do here is take 1/2 or 0.5 raised to the 6th power. So with my calculator, I just type in 0.5. And then there's like a little caret key to raise something to the 6th power. When I take 1/2 to the 6th power, I get 0.015625, and then I multiply that times the amount that you started with, and so the amount remaining after 48 days is going to equal 0.03. It's like 328,125. I'm gonna round it right here, or right after this 3. So it's 328. So I'm gonna round it to 33, and it's in grams, of course. So we've gone from 2.1 grams, 6 half-lives later, which is 48 days. The amount of iodine 131, the radioactive iodine 131 that's remaining, is only just a small fraction, 0.033 grams. And a general rule, by the way, is when this fraction gets to about 10, so you know the time over the half-life is about 10, so that you put a 10 in here. That's not this problem, obviously, but when 10 half-lives have gone by, whatever the substance is, that is generally considered enough time for the radioactive material to be safe again. So you need 10 half-lives. Now some things have half-lives. You know, this is pretty simple because it's only 8 days. But there are some things that have half-lives in the thousands of years, and so it would be 10 times that. Or there's some half-lives that are in the millions of years, or even billions of years. So you know you'd have to multiply that times 10 to reach the amount of time for that substance to be safe. Safe to be around, where it's basically indistinguishable from background radiation. All right, let's do another one of these. All right, so here's another problem. We're going to use the radioactive substance strontium-90, which has a half-life of 28 days. Let's say that we have a starting amount of, I don't know, I'll use, 4.3 ounces, okay, just to show you that, you don't have to be in grams or anything like that. So there's the half-life, there's the amount that you start with, the amount of time that goes by. Now this time we're going to, it's not going to go, 28 years is not going to go evenly into this. So let's say 75 years. 75 years go by. So that's, like an average human lifetime. If that amount of time goes by, how much of this strontium-90 remains of the original 4.3 ounces? And so the calculation is well, we could do this. We could do the well, here, let's just do it the way. So the amount remaining is going to equal the amount that we started with, which was what, 4.3 ounces. 4.3 ounces, and so the answer is going to be in ounces, times 1/2, and now we're going to raise the 1/2 to the to the amount of time that's gone by, so it's 75 years. The years are going to cancel, divided by the half-life, which is 28 years. All right, so if we did 75 over 28, that turns out to be about 2.68. If we round it right there, I got like 2.678. And anyhow, so what does this equal? All right, so it's going to be 4.3. Well, let's do this. So we got to take 0.5 raised to the 75 divided by 28, which of course is 2.68 roughly. So I'm going to do it exactly. Raised to the 2.67857 blah blah blah. So what I get is the fraction anyway. 1/2 raised to this power is about 0.156. I multiply that times the amount that I started with, the 4.3 ounces, and I get what's remaining after 75 years is 0.67, roughly 0.672 or something like that. But that's fine, 0.67, and it's ounces. All right, so there's another example of half-life. Right, and so it goes, for half-lives. I'm going to get back into this PowerPoint, try to finish this up. All right, so there are different ways of measuring radioactivity. The Geiger counter was one of the first ones that was created. Remember, Geiger was was a colleague of Rutherford back when they detected the nucleus. They found the nucleus. There's different measurements. There's what are called millisieverts. There's rad. There's lots of other ones. Becquerel. There's Curies and things like that. REM or millirem are good ones for basically measuring how much the human body can take. And here's something that was discovered, of course, at the very end of World War II, after the United States had dropped the fusion bombs, the fission bombs, the atomic bombs on Hiroshima and Nagasaki. And basically, the human body is exposed every year, no matter what. I mean, it's just background radiation that comes from the ground, comes from space. So there's really nothing you can do about this, to about 0.13 rem every year. And we think that the government has determined about half a rem is the upper limit of what people should be exposed to. When you get into the really high dosages of radiation, 25 rem, you're going to start to see radiation sickness begins. 100 rem is you really start to see people actually getting sick all around you. I mean, the 25, they might get sick, they might not. When you get up to a 500 rem, about half the people will die. And then if you're up to the level of about 1,000 rem, every human, no human can handle 1,000 rem. All right, so this is let's talk about nuclear energy. One of the things that came out of World War II, after World War II, and building a bomb, a fission bomb, or also known as an atomic bomb, is that we realized that. All right, so this was the discovery of how to build a bomb. You take this is what they started with, was uranium-235, which of course is a isotope of uranium. There was a guy in England named Leo Szilard. He won a Nobel Prize for this discovery, which he classified immediately. He was a Jew who had left Europe because of the rise of the Nazis in the 1930s, and he could see, every Jew could see the writing on the wall, and if you could afford it, you got out of Europe, because things were not going to go well. Anyhow, Leo Szilard was working in London and in the early 30s, and he realized that if you hit uranium-235 with a slowed down neutron, a single neutron, but you slow it down, you would come up with, and he even came up with this term, a chain reaction, where the splitting would continue, and it would be literally an explosive thing, an explosive force. And of course, after that, he went to the United States and talked to Einstein, who was a lifelong pacifist. Although Einstein was from Germany and he knew what was going on. He also was a Jew, and he knew what was going on. And he and Szilard actually wrote a letter to Franklin Roosevelt. And Roosevelt, when he finally got this letter, realized we needed to do something. Because Szilard convinced Einstein that the Germans were going to be working on this, and indeed they were, but they never got as far as the United States did, because they never realized this part about slowing down the neutron. All right, let's stop there.